Hello, good morning, all of you. Maybe for the last 2 to 3 days, you might have seen me with a bit dull face. Try to change my face and bring a small smile into that. Good morning, all of you. Electrostatics, an ultimate topic. Capacity and capacitors is today's topic. We'll go in a sequence. Capacity definition, capacity of conductor, then we define capacitor and the important expressions for capacitor, like expression for intensities, potential difference, capacity, the effect of dielectric, and so on. Right? So to begin with, the definition of capacity, the ratio of charge to potential. SI unit is Coulomb per volts and that is Farad. SI unit is Farad. Farad is a very big unit. We never get any conductor whose capacity is of the order of farads, not a practical unit. Therefore, generally we use the submultiples like microfarad, the picofarads, micro 10 raised minus 6, nanofarad 10 raised minus 9, picofarads 10 raised minus 12. Those submultiples generally we use. Now, capacity of a conductor is the ability to hold the charge, literally speaking, but in the class I have told you, remember, it is the charge required to increase the potential of a conductor by unity. That is how we have defined there. Now, capacity of a conductor depends on two aspects. Number one, size of the conductor. Remember, size of the conductor and then the surrounding medium. The medium which is surrounding the conductor also affects the capacity of a conductor. The capacity of a conductor never depends on charge on the conductor, remember. Now, when it comes to the question of size of the conductor, remember a very important expression we are giving it for a spherical conductor, which is most probable question in our NEET and CET. Therefore, here we are given expression for capacity of a spherical conductor. I take a conductor in the form of a sphere of radius capital R, then capacity is 4 pi epsilon naught R. So remember, this 1 by 4 pi epsilon naught value earlier we have used in Coulomb's law, which is 9 times 10 raised 9 we have given. Then what is the magnitude of 4 pi epsilon naught? It is 10 raised minus 9 upon 9. This 4 pi epsilon naught I am writing it as 10 raised minus 9 by 9 times R. Now this expression 10 raised minus 9, we will see the submultiple. This speaks why we cannot have capacity of the order of farads, because of this number 10 raised minus 9 always gives this capacity in microfarads and nanofarads of the order. Now you can calculate for a given radius the capacity of a spherical conductor. Now also one more important result you will find here, that C capacity of a spherical conductor proportional to capital R. C1 by C2 is equal to R1 by R2. Again, if it is not radius, rather you are given areas or volumes. So for such CET's examples, I am showing you these results. See here, C1 by C2 is equal to R1 by R2 if you are given radius. If you are given areas, then it will be A1 by A2 under root, because A proportional to R square, R proportional to root A, and if it is in terms of volume, two spheres of different volumes that are given, then you will write it as V1 by V2. I am using this symbol V for the volumes, and this will be the cubed root, V1 by V2 whole rise 1 by 2. Right. So capacity of a conductor Depends upon the size. And one more thing, when it comes to the question of the surrounding medium, the nature of surrounding medium, we'll discuss in the due course. Now, immediately we will get into this popular topic of parallel plates capacitor. Parallel plate capacitor. Very, very popular. Every time you will see in CET NEET a question based on the capacitors. Now here, this is a small arrangement. Identical plates, each of surface area capital A. One is a positively charged plate, other is a negatively charged plate. Now, the parallel separation between them here is D. Now, here there is an electric field set up between the two plates. An electric field directed from positive plate to negative plate you will find here, right? And please do remember, these distances that we have shown in the figure are in the macroscopic, it's a microscopic picture you can say. Sorry, you can say it is a magnified picture you can say. In the practical cases, this distance will be very, very, very small, of the order of few millimeters. Now this is an electric field that is set up. So that is electric field intensity. Now I am writing using that Gauss law. You remember integral E bar dot dA bar is equal to Q by epsilon naught for the flux. So using that expression, E, the intensity vector, is Q by A epsilon naught. Important expression. See, it is not a memory. You are using the Gauss law and you are writing this relation. Now once you got this electric field, the other things now easy. Nothing as such memory. Now here I am using potential difference between the two plates. V is equal to ED, another relation between field and potential. So V is equal to ED because here it is directed from positive plate to negative plate. Therefore V is equal to ED, D the separation between the plates. So the result QD by A epsilon naught. Right? So you can here find what are the different parameters on which these things are now depending. Now, definition of capacity Q by V. Therefore, for a parallel plate capacitor, capacity Q by V will give you A epsilon naught by D. You can here see this term is independent of charge. Depends only on capacity of the capacitor. Depends only on. Earlier we said the same here. You can find A, the size of the plates, B, distance between the plates, and of course epsilon naught. You should be remembering the value of epsilon naught 8.8 into 10 rise minus 12. Remember? And also do one more time recollect the SI unit and also direction formula. Right? Capacity of a capacitor C proportional to A by D. One more important result. Comparison of capacitors for given data. And now we are discussing about the effect of dielectric on the capacity of a capacitor. Earlier we told that the capacity of a capacitor depends upon the surrounding medium. Here you have found the electric field intensity E bar directed from positive plate to negative plate. Now what is the change that will come here? Now one more figure you will find here. I have shown. This is again a capacitor, parallel plates, each of surface area A, same parallel distance B between the plates. And now here I have used one dielectric slab. This is a dielectric slab I have taken. Same surface area as that of the plates, and this is of thickness T. Remember, D is the distance between the plates, and this T is thickness of the dielectric, and this dielectric has a constant K. So all the parameters with their regular meaning: T the thickness of the plates, K the constant of the dielectric. Now here, when a dielectric is placed, there is a phenomena that arises called dielectric polarization. So polarized charges will now appear, not induced charges. Remember, the charges inside the dielectric are polarized charges. That dielectric polarization will set up an electric field inside the dielectric. Now if you watch this figure carefully, what you find is Outside the dielectric, you have a field directed from positive plate to negative plate, whereas these polarized charges producing field are opposite to the external field. I am now writing as E naught, which you will find which is anti-parallel to the external field E. As a result, the net intensity will be E minus E naught, which is decreasing. The effective field decreasing, therefore effective potential difference also decreases. Remember what is the principle of capacitor? Increasing the capacity by decreasing the potential. No increase in size, decreasing potential, capacity can be increased. Thus here what happened? As a field getting weakened, potential difference decreases and hence capacity of the capacitor increases. Now I am writing an expression for the capacity with the dielectric. Capacity with the dielectric, please be careful about the expressions that I am writing. Here in the figure you will find this is a dielectric which is partially filled. You can see this figure, right? The complete space between the plates, capacitor plates, not filled with the dielectric. I have shown partial filling. If D is the distance between the plates, T the thickness less than D I have shown here. For that you will get the capacity, new capacity. C dash is A epsilon naught upon D minus T into 1 minus 1 by K will be the result. We don't need any derivation part. You do remember the result. D minus, you can see the denominator term, D minus T into 1 minus 1 by K. And since the denominator decreases, C dash becomes C dash greater than C. And now put T is equal to D, that is complete filling. Then this expression for T is equal to D, you will get the C prime is K times A epsilon naught by D. That is what is becoming K times C dash is equal to Kc. Here the expression you will get less than Kc. See, remember, C dash greater than C but less than Kc. But here in this case, C dash is equal to Kc for complete filling. Now here, an important thing that we can observe from this expression is, denominator term, earlier it was A epsilon naught by D, you see here, A epsilon naught by D, but here it is D minus. What does it mean? It does not mean that the capacitor plates are coming closer, never. It does not mean capacitor plates are coming closer, I have repeated the statement. Rather, we will definitely say, effective distance between the plates has decreased. That effective distance decreased by, what is the factor you will find here? T into 1 minus 1 by K. Now this is an important thing. While you are looking for some examples, the solution is based on this particular term. What is that? The factor by which the distance has to be changed. See, remember here, T into 1 minus 1 by K is the factor by which effective distance is decreasing. Supposing some of the examples, you will find them in your assignments, that even after placing the dielectric, for the capacity to remain constant, what is to be done? Is a question. In such cases, now tell me what is the answer? Since effective distance has decreased, we have to increase the separation. Now what should be the increase in the separation? Then the answer is T into 1 minus 1 by K. Now here examples can be given both in terms of symbols or in terms of numericals. So carefully watch and practice your assignments. Now I'd like to show you all the important results for a parallel plate capacitor. Just listed out. Watch it. Now positive plate, negative plate, an electric field from positive plate to negative plate, right? Now here, look at all the expressions, important expressions. The intensity term, the intensity between the plates, Q by A epsilon naught. I have been given even in terms of sigma Q by A, the charge intensity, sigma. Now E independent of D is another result. See, this is what is your observation skill. Look at the RHS and LHS and go on finding the constant terms, the variable terms, the potential difference between plates. V is equal to ED. Remember, if I simply remember one expression, what is that expression for E? All the other parameters that follow is not a memory, is a very small simplification, right? V is equal to ED relation, so potential difference. Already we have got an expression, capacity A epsilon naught by D. And now that comes another important aspect of energy stored in capacitor. Remember, capacitor is not a device that stores charge. Never we should say that. In fact, what is the net charge inside a capacitor? It is always zero. Why? One plate with plus Q, the other plate with minus Q, net charge is zero. Not a device to store charges, but it is a device used to store energy. You remember, we produce intense electric fields at low potential. That is what is the beauty of capacitor, right? Intense electric field at low potential. Now here in this case, in the charging process, the battery does work. The battery does work in charging the capacitor, and that will store as electrostatic potential energy. And you have a very popular expression, U is equal to half C V square. The same you can write it as QV by 2, or even you can write it as Q squared by 2C. All expression. Again, it is not three expressions I am writing. What is the definition of capacity? C equal to Q by V. Q is equal to C, right? So alternate forms I am now writing. Here C V squared by 2. One CV I have taken as Q, therefore it is Q V by 2. And again I write it as C is equal to, substituted, it is Q squared by 2C. So all the expressions very popular for our exams. Remember. Now again I am telling you one expression we need to remember is that of intensity. All the other things will follow automatically afterwards. So this is what is the energy stored in the capacitor. And since already I know expression for C and V, you can substitute and get this expression. U is equal to Q squared D by 2A epsilon naught. Keep watching your RHS and LHS and understand all the parameters. And now here, this is the energy stored in the entire space between the capacitor plate that I have taken. Sometimes there is a terminology in your question says energy density, the energy per unit volume. I am not taking it as energy per volume, energy density. I am using a symbol small u here, which will calculate by volume you will do. So then the expression is half epsilon naught E square. So this is also an important expression to be remembered. Now, since you know the energy expression, now you can also write one more expression. In the capacitor, the two plates are there, one a positive plate, the other one is negative plate. Therefore, there exists an attractive force, coulombic force F. And how to calculate that F? Well, the same expression for potential energy conservative force. You remember, U is equal to F equal to du by dx. That expression, that derivative will give you the force between the plates as Q squared by 2A epsilon naught. Now here you find the parameters where some of them depend on charge, some of them does not depend on charge, some of them depends on both the distance and areas, and some of them independent of distance. All those expressions now you can here find. And one more important topic I will discuss, that is the effect of dielectric. This is an important case for our CET NEET exams. Now here I am discussing it as two cases. What is that? First case, dielectric filled. I am writing for complete filling, remember. Writing for complete filling of dielectric without disconnecting battery. Without disconnecting battery. What are the results? The keyword is complete filling of the dielectric without disconnecting battery. In this case, since battery is not disconnected, what happens? V dash will be same as V. I am using all initial values with the V, E, C, U like that, and after introducing the dielectric, I am using the same with primes, V prime. So the new potential difference after introducing the dielectric. V dash is equal to V. Why? Because we have not disconnected the battery. But capacity C dash is equal to Kc. Capacity becomes K times is the earlier result. Whenever dielectric is introduced and complete filling, capacity becomes K times. Since capacity has increased, it can accept more charge. Remember, capacity has increased does not mean that always the charge increases. It should not be taken like that. But in this case, capacity has increased and to supplies the charge, the battery, and it is not disconnected, and hence Q dash is K times Q. Q dash is K times Q, and now U dash, the new energy. Earlier we have told in the process of charging, work is done by the battery and that will store as energy. Now in this case, since additional charge is now flowing, after the dielectric is filled, additional charge will flow from battery to capacitor, and hence additional work is done, and hence energy on the capacitor increases. U dash becomes Ku is the result. Why U dash is equal to Ku means? Because again additional charge from battery to capacitor is the result. Now in the same case, suppose I do after disconnecting battery. Now again the electric is filled, complete filling, after disconnecting battery. So what will be the results? What will be the small changes that we observe? Is first, earlier we have seen as a effect of dielectric intensity and hence potential decreases. So V dash is equal to V by K. So V dash less than V. But the same result, C dash is equal to Kc. C dash greater than C. This is the same in both the cases, whether we are introducing without disconnecting or after disconnecting. C dash is equal to Kc. Now remember, Q dash is equal to Q here in this case. Why? Though the capacity has increased, the charging battery is disconnected, therefore additional charge cannot be supplied to the capacitor. Therefore Q dash is equal to Q. But since this potential has decreased, energy also decreases. U prime I have taken as U by K, U dash less than U. So go through all those expressions which are remaining constant, which are increasing, which are decreasing, like that. And please in example don't miss this term after disconnecting or before disconnecting. Here comes a combination of capacitors, series combinations, parallel combinations, and also mixed combinations. Very, very simple points. So it's a very, don't take it anything as a memory, you just work it out and it will be a very good help in the examination hall. See here I am beginning with the series combination. What is meant by a series combination? It means don't ever think that side by side. No, it's not like that. Remember the statement in your notebook? It is undivided charge. The group of capacitors, group of condensers in which charge is undivided, all such cases it will be series combination. So undivided charge is the rule for the series combination that is shown here, and you can see I have connected between the points A and B. A at higher potential, B at lower potential. I have considered VAB equal to V. Now here please look at this charge distribution, alternate plus minus you will find such that undivided charge, therefore Q1 equal to Q2 is equal to Q3 is equal to Q is common charge. Please don't ever say same charge, it is common charge which is undivided. This Q is the charge supplied by the battery, it is not same, it is the common charge. Whereas in the series combination, potential divides Among the capacitors here, among the capacitors, potential divides. And potential divides rule everywhere, wherever you come across potential divider. For a capacitor, the rule is V proportional to 1 by C. Since I have used 3 capacitors, now I am writing it as V1, V2, V3 ratio, inverse ratio 1 by C1, 1 by C2, 1 by C3. You can write it as V1, how many parts? C2, C3. V2, how many parts? C1, C3. V3, C1, C2 parts, like that. So this is how we divide. Now, most of the examples we come across potential divided between 2 capacitors. Please see here. Now you can see here, this is total volts V divided between C1 and C2. Right? Capacitor C1 and C2, only 2 capacitors. Then C1, how many parts it will get? C2 parts out of total C1 plus C2. Therefore, V1 is total volts times C2 by C1 plus C2, and hence V2 is equal to like that. So if it is 2 capacitors or 3 capacitors, I have simply shown the parts. Supposing in this case, what is V1? Out of total voltage V, it should get C2, C3. What are the total parts? It will be like C2, C3 plus C1, C3 plus C1, C2. Likewise. Now in this we are calculating the effective capacity, right? All the 3 or any number that are in the series in the group will form as a single capacitor whose capacity I have taken it as, let me call it as CS. As for series I am using effective capacity is the expression. Effective capacity, this one is the expression. And again I am writing it for 3 capacitors. It will give, please do remember you are writing 1 by CS, not directly you are writing CS in this case. And I am showing you directly you can write CS as C1, C2, C3 upon C1, C2 plus C2, C3 plus C3, C1. But most of the times you will find 2 capacitors series combination. Then you will use it as C1, C2 by C1 plus C2. And this type of expression will reveal that effective capacity CS is always less than the least value in the group. Supposing there are 3 capacitors or 5 capacitors, any number, in that group, whichever has the least capacity, less than that will be the effective capacity. Supposing if you take 3 microcoulomb, 6 microcoulomb, what will be the result? 3 into 6 by 9, that will be 2, less than 3 microfarad you will get, right? So effective capacity is less than the least value. And now this also another point, please do remember, supposing if I consider n identical capacitors, each of capacity C, all of them in series, then the effective capacity I will write as C by n. Now when you are solving the examples, one more important clue I am giving you to remember. Now here, undivided charge Q1, Q2, Q3 ratio is 1:1:1, that is what you write. Whereas potential division, V proportional to 1 by C, V1, V2, V3 ratio. And now, interestingly, you will find, supposing if the energy divides among the capacitors, then U proportional to 1 by C, inverse ratio, lesser capacity, that capacitor will acquire more energy. So potential and energy both are in the same ratio in the case of series combination. And now let us do the parallel combination also now. Undivided charge will be the series combination. Now undivided potential. I repeat, undivided potential, which we also call common potential. The common potential points, undivided potential, it becomes the parallel combination of capacitors. Now here I have shown C1, C2, C3, a very regular method of showing. This is not the only unique method that it is shown. Do remember, it's a very regular representation. I have also shown the same between the points A and B, supposing A at higher potential and B at lower potential. Now A is a common potential point for C1, C2, C3. It's a common point. Similarly, B is also a common potential point for C1, C2, C3, and therefore we have taken the undivided potential, the common potential difference. The ratio V1, V2, V3 is will be 1. Now here we will find here the charge is divided. In the series combination, potential divided in the inverse ratio of capacity. Here the charge divides, and charge divides in the ratio of capacity. More capacity, more charge, less capacity, lesser charge. And therefore I am writing Q1, Q2, Q3 ratio, C1, C2, C3 like that. So examples, charge division, expression I am showing you here. See this, suppose the charge Q is split between two capacitors C1 and C2. Then on C1 the charge will be Q times C1 by C1 plus C2. Suppose if 3 capacitors, you write Q times C1 by C1 plus C2 plus C3 like that. One more term will be added in the denominator, but the numerator remains the same. So charge is now dividing in the ratio of capacity. Now look at this effective capacity. I am writing as CPP for parallel. You will see capacity is increasing. C1 plus C2 plus C3, what does it mean? It will be greater than the highest capacity in the group. Earlier in the case of series combination, the effective capacity is less than the least value. Now in the case of parallel combination, the effective capacity will be greater than the highest value. Supposing I take 3, 5 and 20 numbers in microfarad as capacitors and all of them in parallel, then the answer is 3 plus 5 plus 20, it becomes 28, greater than the highest number 20 in the group like that. And now again, n identical capacitors, each of capacity C connected in parallel, the effective becomes n times C. So I am again showing you here the one more point, that same as ratio of potentials, 1, ratio of charges in the ratio of capacities, and energy also in the ratio of capacity. In the series combination, you have seen U energy division proportional to V. U proportional to V was the result. And here in the case of parallel combination, U proportional to Q. See, Q proportional to C, U proportional to C, therefore I can write a result U proportional to Q. So U1, U2, U3 ratio will be C1, C2, C3 like that. Remember, in the series combination, we are increasing the voltage ratio, voltage rating. We are increasing the voltage rating, but capacity is decreasing. Now in the case of parallel combination, we are increasing the capacity rating but not the voltage rating. Series combination, we are obtaining higher voltage rating at the cost of capacity, whereas in the parallel combination we are getting higher capacity rating but at the cost of voltage. That is why we now talk about another combination which we call mixed combination, where we achieve both the things, that is higher capacity and higher voltage. Now please see this. Here I have shown one mixed combination. The case of all identical capacitors, each capacity, see here is shown. See, this is a small network that I have shown. Here 1, 2, 3 like that. X capacitor, all of them capacity C and voltage rating is V. Do remember, I am writing C for capacity, V for voltage. These are capacity rating and voltage rating of each capacitor. X capacitors, all of them in series. Then Y such rows, I have connected all of them in parallel. So each row contains X number of identical capacitors and we have connected Y such rows in parallel. And now we will make use of both the series combination and parallel combination rules here. Now for each row, what will be C dash? For each row, effective capacity will be C by X according to our earlier rule. V dash is equal to XV. Capacity decreases but potential increases. This is for each row. Now for n rows in parallel, again the same rule here we have taken. What was that? N identical parallel, effective capacity is n times C. For in such case, what will be effective capacity of all the n rows in parallel? Then it becomes Y times, because the number here is Y in parallel. So Y times C by X. And what will be the V effective? Again, since same common PD of all the rows, V effective is equal to X times V. C effective is equal to Y by X times C. So these are the results. Y by X times C. Now by suitably taking the values of X and Y, we can have required capacitor. That is a capacitor of required capacity rating and also voltage rating. That is what is the mixer combination. So this is a very brief information regarding capacitors. Go through all the topics, prepare thoroughly, and in tomorrow's class we shall do examples based on all these concepts. Once again, a very good day to all of you.